Have you ever gazed up at the night sky and wondered what secrets are hidden within the vast, silent darkness? While we see stars, planets, and nebulae, some of the most powerful and fascinating objects in the cosmos are completely invisible. They are black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. For decades, black holes were mere mathematical predictions, the fantastic stepchildren of Albert Einstein's general theory of relativity. Today, they are a proven reality, photographed, measured, and central to our understanding of how galaxies form and evolve. In this detailed exploration, we will journey across the cosmos to understand what black holes are, how they are born, how they alter the very fabric of reality, and what it might be like to encounter one. At its simplest, a black hole is not a hole at all, but an extraordinary amount of matter packed into a very small area. Think of it like this. If you were to squeeze the entire mass of the Earth, all its oceans, mountains, and cities, into a sphere the size of a single marble, you would create a black hole. This extreme density is what creates a gravitational pull so strong that it consumes everything nearby. A black hole represents the ultimate triumph of gravity over every other force in the universe. To understand why they are invisible, we need to understand the concept of escape velocity. To launch a rocket off Earth, it must travel at about 11 kilometers per second, 7 miles per second, to break free from Earth's gravity. The stronger the gravity of a planet or star, the higher the escape velocity needed. A black hole is an object where the gravity is so extreme that the escape velocity is greater than the speed of light, 299,792 kilometers per second. Since nothing in the universe can travel faster than light, nothing can escape. This is why black holes are black. They don't reflect or emit light, they trap it forever. A black hole is generally defined by three main parts: the event horizon, the singularity, and the ergosphere. The event horizon. This is the critical boundary or point of no return. It is not a physical surface like the crust of a planet. It is a mathematical demarcation. Once any object, be it a molecule of gas, a planet, or a photon of light, crosses this threshold, it is forever lost to the black hole's interior. If you were outside the event horizon, you could potentially pull away. Once you cross it, all paths lead inward. The singularity. According to our current understanding of physics, all the matter that falls into a black hole is crushed into a geometric point of zero volume and infinite density at the center. This point is called the singularity. Here, the laws of physics as we know them break down completely. Space and time cease to exist in any meaningful way. It is a region where current science cannot go. The ergosphere, for rotating black holes. If a black hole is spinning, the event horizon is surrounded by an oval-shaped region called the ergosphere. In this space, the black hole's immense spin drags the very fabric of space itself around with it. It is physically impossible to stand still within the ergosphere. Space itself is moving you. Where do these monsters come from? The most common black holes, known as stellar-mass black holes, are the catastrophic final act of a massive star's life. Stars spend their lives engaged in a delicate balancing act. They have enormous mass, and gravity is constantly trying to crush them inward. However, the immense pressure and heat at the star's core trigger nuclear fusion. This fusion creates a powerful outward pressure that pushes against gravity. For millions or billions of years, these two forces are in balance. The balancing act cannot last forever. Eventually, the star runs out of nuclear fuel. First, It exhausts its hydrogen, then its helium, and so on, fusing elements up the periodic table until it reaches iron. Fusing iron consumes energy rather than releasing it. When a massive star attempts to fuse iron, the outward pressure suddenly vanishes. Gravity wins instantly. In a fraction of a second, the entire star's mass collapses inward at a quarter of the speed of light. What happens next depends on the initial mass of the star. Medium mass stars. If the star is up to about 20 times the mass of the Sun, the collapse is halted when the nuclei of its atoms are crushed tightly together, creating a ridiculously dense object called a neutron star. High-mass stars. If the star is truly monstrous, more than 20 times the mass of the Sun, nothing can stop the collapse. Not even atomic forces can withstand the gravity. The star collapses completely, crushing itself through its own event horizon and into a singularity, leaving a black hole where the star's core once was. This collapse triggers a massive explosion that blasts the star's outer layers into space. This event is a supernova, one of the most energetic events in the universe, momentarily outshining an entire galaxy. While stellar-mass black holes are born from star collapse, there is another category of black holes that are vastly larger, heavier, and more mysterious: supermassive black holes. These entities can be millions or even billions of times more massive than the Sun. Scientists believe that almost every major galaxy, including our own Milky Way, harbors one of these monsters at its center. Our galaxy's supermassive black hole is called Sagittarius A. It has the mass of about 4.3 million suns but is condensed into a space smaller than the distance between Earth and the Sun. How these black holes became so massive is still a subject of intense scientific debate. They might have grown by consuming vast amounts of gas and dust over billions of years, merging with other stellar-mass black holes. Or perhaps they were formed from the collapse of massive primeval gas clouds shortly after the Big Bang. If black holes emit no light, how can we possibly know they are there? We find them by observing the extreme effects they have on their surroundings. Watching stars orbit a dark center. We can observe stars in the very center of galaxies traveling at extraordinary speeds in tight orbits. By measuring their orbits, we can apply Newton's laws of gravity to calculate how much mass must be at the center of their orbit to keep them in place. When we calculate this, we find millions of solar masses are required. Yet, when we look at that spot, there is nothing visible. This is how Sagittarius A was first confirmed. Feeding time. The most common way we detect them is when they are feeding. If a black hole is part of a binary system with a neighboring star, or if it is at the center of a dense gas cloud, its gravity will drag gas away from its neighbor. This gas doesn't fall straight in, it spirals inward like water going down a drain, forming a flat disk called an accretion disk. The gas in this disk spirals faster and faster the closer it gets, heating up to millions of degrees due to friction. It glows intensely, emitting high-energy X-rays and light before it falls across the event horizon. Active galactic nuclei, AGN. In some galaxies, the central supermassive black hole is consuming enormous amounts of material. The glowing accretion disk can be brighter than the entire rest of the galaxy combined. These systems are known as active galactic nuclei. In some cases, the magnetic forces in the spinning disk are so intense that they channel some of the incoming gas into two powerful, high-speed jets that blast outwards from the black hole's poles, traversing entire galaxy clusters. Gravitational waves. When two black holes merge, they send ripples through the fabric of space-time itself. These ripples, called gravitational waves, travel across the universe. In 2015, the LIGO Observatory detected these waves for the first time, providing a new way to hear black holes collide. Direct imaging. In 2019, the Event Horizon Telescope (EHT) collaboration published the first-ever direct image of a black hole in the galaxy M87. The image doesn't show the black hole itself. Rather, it shows the shadow of the black hole against the glowing, swirling gas of its accretion disk. This landmark achievement confirmed dozens of theories about the geometry of black holes. The most fascinating aspects of black holes arise when we consider what they do to space and time. According to Einstein, gravity is not a force that pulls you, but the result of massive objects warping the fabric of space-time. Think of a rubber sheet. If you place a bowling ball on it, it creates a deep curve. If you place a marble nearby, it rolls toward the bowling ball, not because the bowling ball is pulling it, but because the marble is following the curve of the sheet. A black hole is like placing an infinitely heavy weight on the sheet, creating an infinitely deep well. Gravity affects the flow of time itself. Clocks on Earth run slightly slower than clocks in orbit. This effect, called gravitational time dilation, becomes extreme near a black hole. If you were wearing a powerful gravity-proof spacesuit and decided to hover just outside the event horizon of a black hole, and your partner stayed in a spaceship far away, something bizarre would happen. To your partner, watching you through a telescope, they would see your movements slow down. Your watch would appear to tick much, much slower than theirs. As you moved right up to the boundary of the event horizon, time for you would appear to slow to a near halt from your partner's perspective. Your partner would never actually see you fall in. Instead, they would see you frozen in time, right on the boundary, fading away as the light you emitted was red-shifted into invisibility by the intense gravity. While time slows for the distant observer, your experience falling in would be quite different. As you fell past the event horizon, you wouldn't notice anything special about that moment. However, as you approach the singularity, you would experience a vertical stretching and horizontal compression called tidal forces. The gravity pulling on your feet would be significantly stronger than the gravity pulling on your head. This difference would become so powerful that it would overcome the forces holding your body together. Your body would be stretched into a long, thin strand of matter. Astrophysicists have a technical term for this: spaghettification. Ultimately, your atoms would be torn apart and deposited into the singularity, adding your mass to the black hole. Black holes remain the universe's ultimate mystery. While we have photographed their shadow and heard their collisions, they still hold fundamental secrets about the nature of space, time, and gravity.